there are flows that are steady, and a good example of a steady flow. Go. Oh, well, okay, but if you don't give it to her, if she doesn't come in, you've got to give it, because I don't have any extras of this. So, because I had to make them at the last minute during class yesterday, and I didn't have, I was thinking I wouldn't have time for extras. Anyway, where was I? Okay, steady flows like a river. It just keeps flowing along. Unsteady flow is where the material changes velocity over a short time, like waves. It speeds up, it slows down. It goes forward, it goes backward. The direction and speed of the water changes over time. And finally, there's uniform flow. And uniform flow is like flow in a channel. The geometry of your flow doesn't change. But non-uniform is where the flow changes with distance. So a great example is a stream flowing into a reservoir or lake, where it comes in and spreads out and slows down. So you measure it here, it's different than measuring it down there. And these are, so you can have any combination of these. So for example, steady uniform flow would be a river. Unsteady uniform flow would be say a beach, where the water isn't changing, it's just going back and forth on the beach. Steady non-uniform flow would be a river flowing into a lake. And unsteady non-uniform flow, maybe like waves in a tidal estuary, where it's going in and spreading out, but also changing because the waves are moving back and forth. All right, those are just words you should know. There's certain laws that have to be followed. We don't lose mass, we don't lose momentum, we don't lose energy. It's changed. So the classic laws of physics. And let's go with it. So any questions about that? That was the kinds of flow, the constants, all of those things from the intro part. Anyone have any questions on that? Okay, so now we're going to do the fun part. Energy and flow. And we're going to talk about first, and the reason we do this is moving fluids lose energy. They expend, well, they transfer energy to heat energy and lose energy. And so what we're going to do is talk about first the types of energy in flow. Oh, by the way, here's the symbols we'll use for equation. One of the weird things in hydrodynamics is people use U for velocity instead of V. And the reason we use U for velocity is we keep V for the velocity of a particle. You know, the physicists always have the little table tennis ball, not table tennis, pool balls whacking each other, and they use V. So we keep that V for the grains that are bouncing or flying or rolling down a stream, and use U for the velocity of the water. Everything else is pretty standard. Rho is this funny looking P, and is the standard physics symbol for density. We use rho W, or just plain rho, for water. And this should read rho S for the density of sediment. And then we use P for pressure. And so don't get those two confused. Any questions? All right. So, here, I want to have some fun. There are three types of energy. An energy in fluids is created by weather. You heat the ocean, You evaporate water from the ocean. Energy from the sun evaporates water that rises and makes clouds. It gets converted, it converts to precipitation in the cloud, hits the land, but now it hits the land up high in the mountains. And so here's my raindrop. It's just landed on the surface of the earth, and now it wants to go someplace. It has one kind of energy to start off with, and that's potential energy. And potential energy, if you guys remember from basic physics, is the energy of elevation. It's what has the potential to be turned into other forms of energy by going downhill. So way up in the mountains, water has a lot of energy that can be used as it flows down to the ocean. And I'm going to convert this to some other kind of energy. It's going to start rolling downhill and then goes over a waterfall. That's converting potential energy to kinetic energy. And so we have potential energy, we have kinetic energy, and then in water, there's another kind of energy. Let's pretend we're in Elephant Butte, and we're in a part of Elephant Butte that's 100 meters deep. So what's our kinetic energy in Elephant Butte? In the reservoir? Zero, yeah, it's not moving, it's just kind of hanging. And so up at the surface, we've got water with at least 100 meters of potential energy, right? It's sitting on top of all that water. How come it doesn't go down? What's, huh?
It has to.
Yeah, there's more water underneath it, right? And down here, we've got another cubic meter of water, and that has zero potential energy, right? It's sitting right on the bottom of the stream. So, does it have energy in it?
Well, there's always going to be energy because energy is always being transferred.
It has pressure energy. It has the weight of all that water on top of it. So it's being compressed. It's just like when you go into a swimming pool and you dive way down in the deep end, you can feel that pressure on you. Same with the water. And it's easiest to see if we go to the dam. So here's Elephant Butte Dam now. And either I can let water out over the top, in which case it converts potential energy to kinetic energy and goes sluicing down the top from the top of the dam really fast, right? In fact, this is one of the ways that could make electricity at the dam. The other thing we could do is just make a tunnel down at the bottom of the dam, and then the water would shoot out the bottom, and the pressure energy would be converted to kinetic energy. Does that make sense to everybody? The amount of energy that you can expend is actually the same, because as the kinetic energy drops, or as I should say, as the potential energy drops, the pressure rises in the exact same amount. Otherwise, the water here would be moving down and the water here would be moving up. And it does that now and then, but it does it because temperature changes make this
like the
unstable. If you get the top cold and the bottom warm, this becomes lighter, and so it moves up. It gets.
And we see that in the ocean regularly.
In the ocean, you see big currents that are basically created by the climate of the Earth. You have cold, dense water at the poles. You've got light water at the equator, so things circulate in a very complicated pattern. But that's due to that's real large-scale phenomenon due to the uneven heating of the Earth. Is everybody cool on this? So 3 kinds of energy, but these two are going to be equal, or rather, you trade them off so that when you lose one, you gain the other in equal amount, which means luckily you don't have to deal with pressure because it's always balanced by the pressure, the potential energy. And so we can just imagine ourselves at the surface and be able to calculate that amount of energy all the way down. All right. There is a equation that's used